We're going to discuss linearization of our temperature control lab, and we're going to use this lumped parameter model we have right here in order to do so. This lumped parameter model includes both convection, radiation, and the heat generated. Here we have a linearized model, and we'll be looking specifically at the beta and the gamma parameters in order to determine what those are. Our deviation variables are pretty straightforward. We're going to use the temperature T bar equals 23 and Q bar equals 0 so that we reach steady state and our alpha goes to 0. So we just have these two parameters here. Our derivative of f, the function above with respect to t, and our derivative with respect to q. Now let's do q since it's the easiest. And I'll just write this one out, and the other one I'll do a little bit easier. They're a little bit less complicated. But the derivative of alpha q over m cp, you'll notice that's the only thing that has alpha. This right here is the only thing that has q. So everything else goes to 0, is equal to alpha mcp times dq, which is then equal to 1. So it's equal to alpha over mcp. Now let's look at the other one, and I'll just move this. Let's just grab this. Not that. Let's grab this. Let's just move it down a little bit, give ourselves a little bit more room. We'll look at each one of these terms. Our first term will be negative UA times dt, which goes to 1, plus epsilon sigma A times 4t to the third, taking the derivative of t to the fourth. Then all of this, let me erase that, all of this, one more time with a pencil, all of this is going to be divided by mass and heat capacity. Just to reiterate one more time, what we've done is we've taken this lumped parameter model right here. We have our general linear model right here with the derivatives with respect to both temperature and the heater values, and we're solving for those derivatives. The first one with respect to Q is pretty easy. The derivative of all this function of here with respect to Q is just this constant divided by this constant. So it's alpha divided by mass times heat capacity. The derivative with respect to temperature is just slightly more complicated. The derivative of this term is going to be negative UA, and the derivative of this term right here is going to be negative 4. I didn't really realize I didn't include that negative. Negative 4 times t to the third times these constants right here. So there are terms. Let's look at now how we plug that into the temperature control lab module. Here we have our live script for the temperature control lab. We'll go ahead and scroll down. Here's our linear form discussion as we discussed before in our problem statement. We're going to run the temperature control lab at 75% power for 5 minutes. Here we have the arguments to save the temperature control lab, and then n equals 700. I've gone ahead and I've already run it and saved it in the location and the data so that we don't have to worry about this. This is the step test that will step through and run it at that value and then save it. What we're going to discuss is creating a function named TCLab sim, which returns both a linearized and nonlinear differential temperature for the temperature control lab, and we'll compare that value to the value that the temperature control lab got. So we'll go ahead and we'll look at our function. There's a couple things to unpack here. So the first thing we do is we unpack the temperatures. So in the arguments, we don't have time since we don't depend explicitly upon time, but we do have temperature and then Q as an input. So we unpack temperature as T linear, which is going to be the first one, and T nonlinear, which is going to be the second one. We have our constants, which we discussed before, so I won't go ahead and I'll go ahead and just gloss over those. Here's the part that will get interesting. Our TSS equals our steady state temperature, but for radiation we need an absolute temperature. So TSS underscore K is where we have the steady state temperature in Kelvin. We also have QSS, which is equal to 0, which is the steady state heater setting. We then calculate the gamma and the beta for the linearized model. We discussed that when we looked at the model, but it's the linearized term that we just multiply the deviation variable to. The gamma will be the derivative with respect to temperature of the whole model, and beta will be the derivative with respect to Q. Then we create our linear model. Our linear model is equal to the change in temperature, which is dt, linear. We have gamma times the deviation variable T linear minus T steady state, plus beta times Q minus Q steady state. Our nonlinear model depends on temperature in Kelvin, so we have dt nonlinear with Tk being the temperature in Kelvin. Note here we have T steady state Kelvin to the fourth and temperature in Kelvin to the fourth. Both these quantities have a dot before them, so that to the fourth takes each element within the array and multiplies and raises it to the fourth, I should say. Finally, we pack our results in dt, which is a column vector, which includes the linear and nonlinear model. The rest will be pretty similar to what we've done before. We use ODE 45 to simulate through, with 75 as the argument for Q. Then we'll separate our results and we'll look at the plot. Here we have the plot with the red dots representing the temperature control lab data. We can notice that initially the nonlinear and linear model mirror each other quite well. This makes sense because we're near steady state. As we go further and further from steady state, our nonlinear model will become less and less, will become more accurate, while the linear model will start to deviate. And we notice that happening. The linear model tends to predict a higher temperature than what actually happened, while the nonlinear model predicts quite well what the temperature control lab actually measured. Nonetheless, our linear model still did a pretty good job at predicting the temperature. As far as the magnitude, we're within, I'd say, about 7 degrees by the end. Hopefully it makes sense. We just to review, we're looking at linearized models of our lumped parameter model of the temperature control lab. To do so, we take the derivative with respect to temperature and with respect to the heater setting and make a model that is with respect to both those deviations. To do that, we calculated gamma and beta, and we put it in, and then we used ODE 45 to simulate both linear and nonlinear models. Let me know if you have any questions below. Thanks for watching.